Okay, so Orthomyxoviridae. This is the family of viruses that includes influenza A. It's just common, just the seasonal flu when it's influenza A. There are three types of influenzas in this virus family. There's flu A, flu B, flu C. And so we'll go a bit more into the classification later. But just in order to remember Orthomyxoviridae, just think influenza A. Now, characteristics. There's first is that it's a negative single-stranded RNA virus. So this is so far in this class we've covered the Coronaviridae, which is positive single-stranded RNA, and then Rhabdoviridae, which is negative single-stranded RNA. Then Paramyxoviridae, which is negative single-stranded RNA, and then Orthomyxoviridae, which is negative single-stranded RNA. So it might sound, so I think if going back to the previous virus, we were talking about Paramyxoviridae, and then the thing is, it might sound as if, Paramyxoviridae and Orthomyxoviridae should be grouped together in the same chapter when you're reading a textbook, but it's not, and it's because of a different lifestyle and a different genome that the two have. So that's how they differentiate between the two. And that's, so in terms of the life cycle, like how it replicates DNA and so forth, Orthomyxoviridae is, I believe, a lot more similar to Rhabdoviridae than it is Paramyxoviridae. So just keep that in mind. It will make a lot more sense as we go into it. So going back to the original point, negative single-stranded RNA. Okay, so that's one of the first characteristics about influenza A. Next thing is it's enveloped. Okay, helical nucleocapsid. Helical nucleocapsid. So helical nucleocapsid, that makes it very similar to Rhabdoviridae, Paramyxoviridae. So the two have helical nucleocapsids, but again, they're not, they're differentiated by their lifestyle. Flu is 80 to 120 nanometers, so pretty small. It's spherical. And because it's a negative single-strand RNA, it has to bring in its own viral polymerase for it to transcribe and later on even replicate. Contrast this with Picornaviridae, which came in as a positive single-strand RNA. Polio doesn't need its own virion-associated polymerase because it's literally just a messenger RNA. That's what polio is. It's literally just a messenger RNA. This one, however, is a complement of a messenger RNA, and our eukaryotic machine, our cells do not have the machinery to translate negative single-stranded RNA into mRNA. We don't have that machinery. So in order for flu to even start an infection, it has to bring in its own polymerase. If you don't get this concept, just post it in the comments or something. So I'm going to abbreviate it, just like Dr. Samuel. Virion-associated polymerase. So because it's negative single-stranded, because its genome is negative single-stranded RNA, its genome is not infectious. And that makes a lot of sense. Because without the protein coat, that which has the VAP, it can't do anything. Later on, you'll see that this, when we get to double-stranded DNA viruses, if you isolate the genome, it's actually infectious, but that's for another video. For now, it's flu, non-infectious genome. So I put this down as goes to nucleus. Basically, part of its life cycle, it spends part of its life cycle in the nucleus. I believe that's in the replication phase. Or no, maybe in the transcription phase. Goes to nucleus for transcription. Replication. You'll see why it does this. Basically, flu, it goes to the nucleus because it steals cellular mRNA caps. Again, we'll go into more detail about that later. But the impact of this fact, of this characteristic, is that one of the ways you can treat flu is to give someone actinomycin D, which prevents the cell from making RNA transcripts. You know, and the way that if it can't make RNA transcripts, it also means that it can't make one actinomycin D basically blocks the cell from making the mRNA caps. Without the mRNA caps, you can't make a full mRNA. Likewise, if flu wants to make an mRNA for itself, and it can't make it, and there's no cap, there's no cellular caps being made because of actinomycin D activity, then the flu infection can't go, it can't progress. So I'll write, can use actinomycin D to treat flu. Go over here. GHI. 8 genome segments. So up until now, all the viruses we've covered are monopartite, meaning they only have basically one piece of genome. But influenza is, I guess, polypartite. It has 8 genome pieces. So I mean, it's sort of like a human cell. We have 23, I guess, quote unquote genome segments. Yes, it's 23. Well, technically 46, but so the idea of having multiple genome segments shouldn't be anything surprising or anything peculiar. But the impact of this is the fact that with all the previous viruses, they didn't mutate very much. So you vaccinate once you get one vaccination of the virus, and you're pretty much set for life. Or you're set for a very long time, not for life. However, with flu, because it has 8 genome segments, it can change itself a lot. It can make new serotypes of itself. It just mutates a lot, which means that every year we have to get vaccinated. So you'll see that. Alright, so pause the video if you need to. I'm going to only splitting this up into multiple videos too, just like I did last time. So we'll go into classification next.